morning. It's the physics video lecture once again. Physics 105A, video lecture 36. So we're going to talk about the apsidal angle some more. I'll set it up again. I had given this homework problem. I'm just going to work through the whole thing. It's a really nice opportunity to talk about what this whole thing means. So we're talking about nearly circular orbits, and let's go ahead and set this up. Okay, let's see if we get a better pen. So we'll start with the nearly circular orbit idea. Yeah, so when they're nearly circular, we were just doing our analysis with the effective potential. R0 represents the circular orbit, and when the energy is slightly larger than E0, we have in the Kepler problem fundamentally an ellipse, but generally speaking we just have a non-perfectly circular orbit. Okay, so yeah, those are the R min and R max centered around R sub 0, corresponding to a slightly greater energy. Okay, what we then discovered or defined was the so-called, well actually, let's do this then. So for the nearly circular orbit, we have the radius of the orbit is R0 plus some, I could write delta R cosine omega sub R times T. Okay, I'll leave out a phase, doesn't matter. And this omega sub R is just the second derivative of the effective potential at the circular orbit divided by the mass, square root. And like I said, Kepler potential or Kepler problem, Newton potential, this is just going to turn into a closed orbit, but for a non-Newton potential, this frequency here will not be the same as the angular frequency, so you don't necessarily get a closed orbit. So because of that, we defined the apsidal angle and C was equal to omega sub phi T sub R over 2, and the picture that goes with it, this of course is is exaggerated, so we'll draw this so that we can really see it. So it's the angle swept out between R min and R max. So that angle that's swept out, I'll put it in red, like that. And we quickly saw that we had a really nice formula for this, for just the general potential energy, not the effective potential, but the general expression. Let me go ahead and remind ourselves. U effective of R L squared over 2mR squared plus the actual potential energy. And it is this potential, not the effective potential, but this potential that ends up in our final expression, 3 plus second derivative at the circular orbit times the radius of the circular orbit divided by u prime of R0. And we calculated a couple of examples. Of course, immediately the Kepler problem, Newton potential gave pi over 1, closed orbit. The quadratic potential gave pi over 2, which was also interesting, and that's in our notes. For future reference, we also remind us that we could just as soon, if we're given the force law and not the potential energy, we can, because we have a second and a first derivative, we can of course also write pi divided by root 3 plus f prime of r0 divided by f of r0. I know of some cases where you can formulate a force law where the potential energy is non-trivial to obtain, right? And you don't actually need it because we have second derivative and first derivative. So we can have this as well. We'll just put this in here parenthetically. Okay, so what I want to do now is the example that I had assigned as homework. I'm just going to go through it very carefully because there's a lot to discuss here. So our example now, I'll keep numbering things as long as I remember. The potential energy of a non-spherically symmetric mass distribution for an oblate spheroid. There's some terminology for you. An oblate spheroid, that is, I'll do it as an exaggerated form. So imagine we have something rotating about its axis and it's flattened out a bit because, say, it's a planetary object that's rotating and it's liquid nature to it, okay? So it's actually bulging out here at the equator. So for such an object, oblate spheroid, here's its center, the potential is no longer strictly 1 over r. For an oblate spheroid, I'll even write here around the equator, because now you have some non-symmetry in the mix, but of course a very common celestial object, our Earth, is ever so slightly a non-oblate, or an oblate spheroid. So what we have is u of r minus alpha over r. That represents Newtonian gravity, right? Oh, this whole thing is Newtonian gravity. That represents the spherically symmetric mass distribution plus some beta over r cubed. What's happening here, and we're going to do this next semester, is that one can actually expand the potential energy in powers of 1 over r. And the 1 over r squared does not exist. Okay? So the next power is 1 over r cubed. Okay? 1 over r cubed and so forth. And then the next one after that would be 1 over r to the 4th or 5th. I'm not even sure right now. But yeah, there is actually an infinite series that you can expand it in. But we'll stop at the 1 over r cubed. So yeah, I was thinking about this and realizing that to send you off to do this problem without a little more explanation wasn't so good. So this is the result of an expansion. So what we have to say is where beta is small, and we'll actually get an expression for how beta is small, although we could actually figure it out right here. Where beta is small, and this expression star holds for large values of r. We can't take this down to small values of r. It won't be true. So because it's a series expansion in powers of 1 over r, it's true for large r. And star is valid for large values of r. Okay. So there's no point in drawing an effective potential and adding this expression to it. Okay, we won't be able to make proper sense of it. This is only true out at great distances, or at sufficiently large distances. Okay, so what we want to do now is evaluate this expression here for this potential, and we'll get a very interesting result. We already know if we do the job right, if we get this expression here, it should depend on beta, and of course if we send beta equal to 0 in that new expression, we should just get pi out. Okay, so we already know what we're headed towards. What else should I? Large values are. So I'll just put this as a node. Star is result of expanding the potential energy U of R in powers of 1 over R for large R. We've done similar stuff actually in some of our little Taylor expansions. But good. We're going to do this next semester, so we're not going to leave this in the air. Next semester we'll actually do the theory of potentials and do a little expansion like this. But for the moment, we're just going to take it at face value. And what does small mean? Maybe we can decide right here what small means. What we can do is, here's another node. We could say U of R is equal to minus alpha over R, and then factor out the minus alpha over R, then we have a 1 minus beta over alpha R squared. If I didn't make a mistake, that's right. So minus times minus is plus, get the beta, alpha cancels, R cubed. So yeah, what does small mean? So what we're saying is beta over alpha R squared has to be much less than 1. So yeah, in that sense, this is a correction. And that can only be the case, no matter how small beta is, that can only be the case if R is large enough, okay? As we said right here. Okay, so that's discussed now. Now, what else I want to point out is how this is actually a powerful technique we're going to do, because the astronomers are able to measure these things with great accuracy, and it was known that the orbits around our sun of the planets were not perfectly Keplerian, okay? And the sun is an oblate spheroid, and so these calculations can be done for the sun, and had been, and they still did not match up completely, okay? And you may have heard of Einstein's theory of general relativity. What general relativity did in terms of these calculations, it filled in some missing angle, okay? So the calculation had already been done, okay? This type of expression here determined, and still not perfect, and therefore the theory of gravity had to be completely modified. So yeah, this is a powerful technique and a really interesting and excellent problem. So let's go ahead and give it a try. Now remember, this is the radius of the circular orbit. With this potential energy, we're not even able to solve exactly for the radius of the circular orbit. What's going to happen is something similar to here. For sufficiently small beta, that radius can essentially be taken as the, just the Kepler radius, the Newtonian, or the uniform sphere radius. Okay, we'll see that later. Okay, so what we're going to do is evaluate this. And a couple of interesting things along the way. So So I'll leave this formula up here. What we have to do is calculate the second derivative, calculate the first derivative, do this division 3 plus. So it's going to look kind of messy for a moment, but then we'll see that things simplify. So let's go ahead and give that a go. We have, once again, u of r minus alpha over r plus beta over r cubed. Whether beta is positive or negative, we don't know. And our answer will be sufficiently general, right? It won't matter. But of course, we know alpha is positive. Good, let's take this first derivative is equal to alpha over r squared minus 3 beta over r to the fourth, and the second derivative is equal to minus 2 alpha over r cubed plus 4 times 3 is 12 beta over r to the fifth. So now we're just going to form this u double prime of r times r without even solving for r sub 0. Maybe I should put a note there. I mentioned it, you put it in your notes. Finding r sub 0 is very difficult, and itself has to just be done as an approximation. Which you can see, remember r sub 0 we get from the effective potential. Okay. However, I may put that in there later. I've said it 3 times now. We can just treat this as the circular orbit without even knowing what it is over here. And for small beta, it will be close to the one that we do know. Okay. So continuing on. So we have u double prime of r, and I'm not going to write the subscript. Okay. We'll deal with that later. I'm not going to put the subscript in the circular orbit. It's just there. So yeah, we have a minus, okay, there we go. We have a minus 2 alpha over r cubed, but we're going to multiply it by r, so let's just take care of that. We have minus 2 alpha over r squared plus 12 beta over r to the fourth divided by alpha over r squared minus 3 beta over r to the once more with feeling. R squared, r to the fourth, r to the fourth, yeah, good. So those powers are the same there. Now yeah, this looks bad. You say, I want to add 3 to that and have this expression and take the square root. Okay, that would be a problem, but we can simplify. So for the numerator, let's pull out minus 2 alpha over r squared. And for the denominator, we'll pull out alpha over r squared. So then we'll have 1 minus 6 beta over r squared alpha. And here we'll have 1 minus plus and minus. We'll have 1 minus 3 beta over r squared. Okay, and so we can simplify now. We got the alpha over r squared that can be canceled. minus 2 plus 6 beta minus 3 beta. So good, so we end up with a minus 2 times 1 minus 6 beta over alpha r squared. 1 minus, and there should be an alpha here too, 3 beta over alpha r squared. So that's already a simplification. Now we're just going to name this some kind of x or something. Let me consult here. Okay, I'll put this. I'll keep going here, but we're going to let x be equal to 3 beta over alpha r squared to keep things a little more simple. So we're going to have minus 2, 1 minus 2x divided by 1 minus x. So what was that? That was this thing right here. I'll go ahead and send this up. Now we want to form this expression. Okay, so what do we have? We now have our absolute angle is pi divided by the square root of 3 plus this, I could just put the minus 2 right there. 3 minus 2, 1 minus 2x divided by 1 minus x. And we're going to simplify this some more. Pi will have 3 minus 3x. I'm going to get a common denominator. Minus 2 plus 4x divided by 1 minus x. 3 minus 2 is 1. Minus 3x plus 4x is, so 1 plus x over 1 minus x. So that's pi 1 minus x over 1 plus x. Okay. And that x was given right there in that small quantity. Now, the last thing we have to do is expand this in a Taylor expansion, okay, for small x. So finally, expand f of x equals, in fact, we'll take pi out there, 1 minus x divided by 1 plus x to the 1/2 power to first order. That's going to be 1 plus some constant times x. Okay. F of 0 is 1. No, it's going to be f of 0 plus f prime of 0 times x. And that's all we want, that first term there. So we have f prime of x is going to be 1/2 1 minus x over 1 plus x to the minus 1/2 power. And then the inner derivative is going to be minus 1 over 1 plus x plus 1 minus x times negative 1 plus x, the quantity squared. So we want to evaluate that at x equals 0. And we get 1/2. This just turns into a 1. And then we end up with -1. And then when we plug x into 0 here, we also have -1 divided by 1 squared, -1. So -1 is equal to -1. So this thing here is equal to 1 minus x. Okay. And then smaller terms, but we're keeping x small. Okay. I think I'll just leave myself a little room and get this corrected so when the dust settles, we haven't missed a single step. So what do we have here? Here's our x. Don't want to lose that. So you see, we went through a bit of a messy process, but we're going to have a very clear and simple answer. So the absolute angle, so for u of r equals minus alpha over r plus beta over r cubed. Large R, we found our absolute angle to be pi times 1 minus x, and there's x, so pi times 1 minus 3 beta over alpha r 0 squared. Okay. Now and you see when beta goes to 0, we're back to the perfect closed orbit, elliptical orbit. And depending upon the size of beta, this absolute angle will be greater or less than pi. If beta were negative, it would be slightly greater. And that too can depend on the form of the mass distribution inside there. Now, I said something about this R0 being impossible to calculate. So let's go back to talk about that. So what about the radius of circular orbit? Radius of circular orbit R0. What about that? Okay, let's go ahead and erase this. We have u effective prime of R0, that's supposed to vanish, but u effective prime is equal to, L squared over 2R2, so minus L squared over M R cubed plus alpha over R squared minus 3 beta over R to the 4th. We're supposed to set that equal to 0 and solve for R. Well, good luck. Okay. You need the approximation scheme to solve that. It's a higher order polynomial. So what you have to do is suppose R0 is equal to R subscripts are bad. Okay, suppose radius of circular orbit rho, just to use another letter, such that rho is equal to R0 plus delta R. as long as delta R is small, we can say rho is equal to R0 times 1 plus delta R over R0. And this rho is what would actually be put into here, okay? But it's very close to the original R sub 0, and when beta goes to 0, of course, it vanishes completely, right? Or it's identical. Which means that if we plug this rho into here and do this expansion, we'll get 1 minus 3 beta over alpha R0 squared plus something that is much, much smaller. And since this is already going to be small, this will be second order small and can therefore be neglected. Then, referring back to this thing here, we could have 3 beta over alpha rho squared, that's our circular orbit, is equal to 3 beta over alpha R0 squared times 1 plus delta R over R0 squared, and that's approximately equal to 3 beta alpha R0 squared, 1 minus 2 delta R over R0. Okay. So yeah, you go into this expression with this, and this is already small. The product of this and this is much smaller. Okay. So that's why this is legitimately a good answer. Okay. These are very small corrections, but the astronomers have the ability to measure these small corrections. So yeah, it's a really powerful technique, actually. Okay, I'm going to consult the clock. Good. There are other techniques, okay, in celestial mechanics, but this thing just lends itself to the whole discussion we've been having, okay? And you see there were a number of interesting approximations necessary, but we just kept going and we ended up with a pretty simple expression. The expansion of this finally brings us to here. And you can see we always have control over our approximations. This 3 beta over alpha R naught squared has to be small, much less than 1. If it's much less than 1, then the product of this number plus the delta R over R naught is going to be much, much less. Okay. Okay, so I think that's going to wrap up our central force discussion. And I'm going to start on a new topic, actually something we've mentioned before, but we're going to expand on it quite a bit. So the next major topic is mechanics of systems of point particles. So now we're going to have any number of point particles, so it's going to be mostly theoretical work. We've done 2 point particles. The Kepler problem we actually reduced to a 1-body problem, but we started with 2 particles and we left nothing out. We left no steps out. Okay. But now we're going to do what's called the mechanics of point systems. And this will round out the entire semester, in fact, because that's mechanics, that's classical mechanics. the whole foundation of it, so to speak. So mechanics of point systems. And that means systems of point particles, because our idealization is always that these are point particles for now, point masses. And this time we have a system of n point masses. That's the idea. And now they all interact with each other and they all obey Newton's law of motion. So we just have to write the whole thing down. So here I'll draw, I'm not going to draw all n of them. But instead of 2, we have more than 2, and these are m sub 1, m sub 2, m sub 3, etc. And then they each have a position. So that was my r sub 2, r sub 1, r sub whatever, okay. M sub 5, R sub 5. So yeah, particles and their positions. And they're moving around in space, and they're interacting with each other, and we're even going to add the idea that not only do they interact with each other, but they could all be subject to some external force. For example, if we're just a collection of particles here in this room that could interact with each other, that'd be good, but the external force would just be the gravitational force. Or we could have particles interacting with each other electromagnetically, but they're all in the same space, subject to gravity as well. So that's the idea. And we can write down Newton's law for each of them. So we say m sub I, r sub I, second derivative, is equal to f sub I. So that's the force on the ith particle. And of course, it can be dependent on a lot of things. The most general conditions whatsoever that would be dependent on, R1 to Rn, and then the velocities, and then the time as well. Okay, so that would be the general situation. And then we say I equals 1 to n. Okay, so there's a lot going on there. Next, let's go ahead and break this up a little different. We're going to say that the mass times the acceleration on the ith particle is equal to the force on the ith particle, which we're going to call the external force. The example was just, for example, gravity. It's going to be common to all of them, plus a sum of Fij, j equals 1 to n, j is not equal to I. And these are the forces that these particles exert on each other. So there would be an F12 be the force that particle 2 exerts on particle 1. Okay. So the subscript I is for that ith particle, here, and then you sum over j goes from 1 to n, I go to I, and then this thing is left with a subscript I as well, because you're summing over all the j particles. So that's one way to look at it, and this is the external force common to all of them, but not necessarily identical for all of them, but common to all of them, as opposed to these are the interactions between the system of particles. So these are internal forces, that is to say, internal forces for that system here, this cloud of masses. Could be masses connected with springs, but gravity's more like it. But actually, we could think of, if we thought of a solid object that's somewhat deformable, then these would be the interatomic forces. Okay, so what comes next? I better consult the clock. Yeah, this may be a place to leave it for now, because we have a lot to do. So we're going to develop some general theorems of systems like this and just work our way through to the conservation laws. That's pretty much the rest of the semester. We spend a couple days on these, and then we'll do a review. Everything should tie together really nicely. So, I'll just put here next. Potential energy. And then conservation laws. And everything that we do for these n particles, of course, holds true for 2 particles. And since we'll have already done the 2-particle version, we'll always have something to refer back to from which we're generalizing. Okay. So this is an n particle system. We've done the 2-particle system with a potential energy. Good, we'll leave it at that. See you guys next time.